Thanks very much, Kristen, and thanks for the opportunity to come here. I think quite appropriately the event is focused on solutions and opportunities and so on. So I feel like the bad guy here because I'm going to go back and talk about the problem a little bit, but just remind you exactly where the science is. It's improving all the time. So here we go. I might just stand here rather than walk around like I usually do. So I'm going to give you an update on the science, where we stand in 2014. I'm going to zip very quickly through the first part, which is going to be, maybe I should use this. I've probably done something. Just click anywhere. Okay. There we go. So I'll talk a little bit about the observations that we see and the causes. It's all very familiar to you, so I'll go through that very fast. I'll focus mostly on part 3, what we know about the risks, and I think the main point there is this isn't something for the future. The evidence has now become very strong that we're in the midst of the changes already, and they're changing the risk profile of many of these extreme weather events quite strongly. So I think that's going to be the main part of my message. You've probably seen this. That's the global average surface temperature record around the planet. You can see over the past century and a half it's been heading upwards. A lot of noise in there, and a lot of the skeptics like to focus on the short-term noise. So scientists in that bottom panel have actually done decadal averages to get rid of some of that noise, and you can see how strongly the climate is warming. But the point I want to make is that although this is the subject of a lot of debate, and probably a lot of attacks from the skeptics, for most Earth system scientists anyway, that's not where the action is. The action is actually in the ocean. So when you look at this graph, which comes from the IPCC, for about the last 40 or 50 years, we've had enough data that we can actually look at the ocean. And that's those blue wedges, the upper ocean, light blue, the deeper ocean, dark blue. You see that quite an astounding number. 93% of the extra heat is going into the ocean. 1% is in the atmosphere. So we argue about the 1%. That's because we're terrestrial creatures, not marine creatures. But the real action's in the ocean. And a lot of people, a lot of skeptics anyway, say, well, didn't the Earth stop warming in 1998? Well, there's 1998. And I think anybody can see that the ocean has warmed exceptionally strongly since 1998. So that's where the action is. It's in the ocean. It will equilibrate with the atmosphere in fits and starts, which means we'll go through periods of slower and then more rapid warming of the atmosphere. When you put this in a longer-term perspective, I think one of the breakthroughs of the last couple of years is for the first time we have a 2,000-year reliable temperature reconstruction. And this is surface land temperature around the planet. For the first time, the southern hemisphere gets in. And when you put the southern hemisphere in, the medieval warm period disappears. And that's because the medieval warm period was a North Atlantic phenomenon. It was simply a redistribution of heat, not a warming of Earth. Whereas we see that red line at the end of that record, that's the last century or so, that is indeed a globally synchronous, very strong warming, unlike anything we've seen in the last 2,000 years. So there's a whole wealth of evidence to show that that's not natural variability, that's the human-driven signal. And it's only the beginning of a much higher signal we're going to see through this century. So we could go on and on. Whenever anyone asks you, well, is the Earth really warming? I think the thing to do is rattle off all the different ways in which we measure warming. You can see this on this very nice graphic, which comes from CSIRO and the Bureau, that it's far more than air temperature. It's melting glaciers, it's rising sea levels, it's increasing temperature within the ocean, not just above it, and so on and so on. You're all very familiar with this. We know why this is occurring. This is some model reconstructions of the last century. The reddy, orangey, pinky wedge there is if you put additional greenhouse gases into the models. The purple one is natural variability alone, and the black are the observations. So you can see quite clearly. And there's heaps of other information. I could go on for the rest of the morning. All the wealth of information we have that says this is not natural variability. It's caused by human activities. The major component of that, of course, are greenhouse gases in the atmosphere. And we can look at it continent by continent, which we do there. You see Australia in the bottom right. We can look at it globally. We can look at it in the air over the land, air over the ocean. You see the land is actually warming at a higher rate than the ocean, which is exactly what you'd predict, given the different heat capacities of the ocean and the land. So all this is really well understood. I'm going going to summarize it with two comments from the IPCC. And all you have to do is remember the first phrase of each. Warming of the climate system is unequivocal. That's a pretty strong statement from conservative scientists like the IPCC. And the second one is human influence on the climate system is clear. Absolutely no debate. There hasn't been for decades on those two questions. All right, well, let me go on to the interesting bit, and now I'll focus a bit more on Australia, but I won't entirely leave out the global picture. And I want to talk about the risks. I'm not really going to talk so much about the future. Well, the future comes in. I'm going to talk more about the present, because we now have much stronger scientific information that we're starting to see already the effects of the destabilization of the climate system, and they're being expressed in terms of extreme events. That's the things that affect us day in and day out. So I heard our Prime Minister say not so long ago that there's no link between climate change and extreme events. Well, he's dead wrong on that. I expect he's dead wrong on a lot of other things too, but we'll come any further on that. Okay, heat waves. This is that massive pool of warm air over the summer of 2012, 2013, that's January 2013. All sorts of temperature records broken across the country on that. Unprecedented. We hadn't seen anything like this for quite a long time. So the statistics behind what we're seeing in heat is quite clear. Many of you have seen this nice little diagram of a bell-shaped curve, a distribution of temperature around an average. I don't know what the average is in September for Brisbane, but maybe the average high is in the low 20s. But that doesn't mean every day is 22. So you get some days 17, 18, some days 25, 26, you get a distribution. But if you shift the average to a warmer state, notice what happens to the tails. The very cold days drop off and the very warm days increase at a surprisingly large rate. You get more hot weather and more record hot weather. Now the interesting thing is we now have enough observations to test this. And there they are for Australia. You see exactly that is happening Australia-wide. So on the left-hand panel you see the increase in hot weather. So the very hot days have gone over the past few decades from about 2% of the days to up to 10% of the days. It's a big increase. And correspondingly the number of cold days has decreased. This is even more striking. These are the days, this is an average for Australia as a whole now. These are the days in the top 1% of days. So it's that unusually hot day. Because in the top 1%, and we have 365 days in a year, you would expect somewhere 3 or 4 or 5 days a year would be in that. And in the first half of the last century, you see that's exactly what happened. But look at what happened after 1950. Look what happened, for example, in the last year of the record. We had between 25 and 30 days in the top 1% of the long-term average. So this is definitely not natural variability. This is what happens when you put more heat into the atmosphere. You skew the system toward more hot days. It's not something for your kids and grandkids, although it's going to get worse for them if we don't do something. It's something that's happening to us now, today. And when you look at an analysis of heat waves, and Sarah Perkins at UNSW has done a very thorough analysis of that, you can see that already these are not predictions, these are observations. That heat waves are changing. You can see the little maps of Australia where this is happening. But that top one is virtually everywhere the number of heat wave days is increasing. So hot weather is with us now. The increase in hot weather is with us now. It's part of a global pattern. There you see the Australian pattern, but particularly in the northern hemisphere, there's a massive increase, particularly in Canada and Siberia, of very hot days. If you look at it city by city, you can see what's happening. I happen to reside in Canberra. So if you look at the long-term average of the number of days of 35 and above where I live, it's about 5. But over the last decade, it's gone up to 9.4. That's about as much as was predicted for 2030 in the climate models. So you see in cities like Melbourne, cities like Adelaide, cities like Canberra, we're already hitting the predictions for 2030 in terms of our increase in hot weather. And depending on what we do with emissions, you see that 2030, we're pretty much locked in because of momentum in the climate system. But if we take advantage of the opportunities you'll be talking about throughout this conference, we can actually cap the 2070 hot weather at a much lower level than it would otherwise be. You see, that's why we've got 2 columns for 2070, depending on whether we get our act together or whether we don't get our act together. Well, that's hot weather, and that's closely related to bushfires. Bushfires are complicated because it also depends on the fuel, the amount of fuel load, the condition of the fuel load. And that's tricky because climate change can affect fuel in multiple ways, some positive, some negative. But the most direct link between climate change and bushfires is in high fire danger weather. Those are the days when fires are prone to break out. They tend to be very hot days, tend to be windy days, tend to be days of low humidity, and they often follow dry periods where the fuel oil is conditioned to be drier than it otherwise is. Now we do have data on this, and that's what this map shows. Those big red circles are the Met Bureau's stations that do routinely measure high fire danger weather. They use an index for that, and what they find in those areas, the index has been increasing. This is about a 3 to 4 decadal record, so we think it's long enough to get over the noise. That little inset is the one from Melbourne, measured at Melbourne Airport. But the bottom line message here is in the southeast of the country, where a lot of people live and where a lot of infrastructure is, there is a notable increase in high fire danger weather already. And if we look toward the future, that's what that site in Melbourne airports will likely look like. This is, by the way, business as usual. In other words, we don't get emissions under control. You see the slow increase historically that was in the previous graph, but then you see that ramping up quite considerably later this century. There's a lot of noise in the data there, but the underlying trend is pretty clear. So the bottom line message here is high fire danger weather. The risk is definitely increasing and will likely increase further. Okay, the third one I want to talk about then is the water cycle. And as we know, Australia is the land of droughts and flooding rains, and we see them only a few years apart. The left-hand picture is actually not too far from where I live. That's Goulburn in New South Wales in 2008, 2009, when the dam nearly went dry. In fact, it was virtually unusable. Had a lot of impacts on cultural life. The rugby league season in Goulburn was moved to Canberra because they couldn't play it. They couldn't water the pitches. The pitches got hard and people were breaking a lot of bones. So they had to move down to Canberra. So when climate change starts affecting sport, it's getting really serious. Now, the right-hand panel is the city we're sitting in now. That's Brisbane. And of course, Brisbane's prone to river flooding. And with the La Nina events of the last, well, a few years ago now, I think 2010 to 2012, this was a fairly common view of what the streets of Brisbane look like. So what's happening to our water cycle? It's highly variable. Australia has the most variable water cycle naturally of any of the inhabited continents. Well, what's happening is, in general, it's intensifying. That's happening around the world. It's not just here in Australia. And that's because as you heat the planet, and as I said before, 93% of that heat's going into the ocean. That's important for us because virtually all of our rainfall is sourced from the ocean. I think only about 10% of it's actually recycled from the land. That's different from, say, the Amazon basin, where 50% of their rainfall is recycled from evapotranspiration from forests. But ours comes from the ocean, primarily. So that's why ocean heating is really important. It increases evaporation. A warmer atmosphere can contain more water. The rule of thumb you might want to remember is for every degree Celsius you increase the air, it holds about 7% more water vapor. That's a big number. And that's actually verifiable through satellite measurements of water vapor content. With more water vapor in the air, obviously what goes up comes down eventually, so there's more rainfall. That's what we mean by an intensification of the water cycle. But interestingly, when you look at some of the complex physics behind that, what you find is that when that rainfall comes down, it's now more prone to come down in heavy falls rather than just more drizzle. And again, that's been noted around the planet. There has been an increase in the last couple of decades of heavy rainfall events. That tends to correlate with areas that are getting increased rainfall area, but not in drought-prone areas. So it's not uniform everywhere. So let's look at what's happening in the global patterns. This is a fairly subtle bit of data, but it's fascinating. That left-hand panel is a bit over a century, 1901 to 2010. Now, what you would expect if the climate is stable, if it's not changing, you expect obviously variability year to year, season to season, but you don't expect to see any great changes in wetness or dryness. And that's pretty much what you see in that map. You see a bit of wetting in eastern North America, a bit up in Europe, but most of those land areas are colored white, which means there's no statistically significant shift in the water cycle. But look at the right-hand panel, 1950 to 2010. That's when greenhouse gases really started going up. That's when temperature really started going up. Now you see some patterns starting to set in. around the world. Areas getting wetter, areas getting drier. Overall, the planet's wetting up for the reason I just talked about. But it's the distribution that matters. So obviously you can see the Mediterranean's getting really dry, northern China's getting really dry. It shouldn't be. That's probably affected by air pollution in addition to climate change. Another reason the Chinese really want to get this under control. But let's now focus on Australia, and I'll give you a much higher res picture. You can see the pattern starting to emerge in Australia. And that's what it looks like in higher resolution from 1970 to 2010. If you actually add all of that stuff up overall, we could become slightly wetter, which most Australians wouldn't believe. But most of the rain is falling in areas where we don't live and where we don't have agriculture. So the ones obviously southwest WA, southeast, where there's increasing evidence there's climate change signals in those areas, and then up along the Queensland coast from here extending northwards. And that's complicated because we can't quite yet see a convincing evidence for a climate change signal. Doesn't mean there isn't one, just means there's a lot of noise and natural variability there. But the southern part of the country, we're pretty sure that's going to be with us for a while. So let's look at that in more detail. And the Bureau's published some really interesting maps just earlier this year. This is a map of rainfall change over pretty much the past 2 decades, I think from mid-1990s. Now this is summertime, this is the northern wet season. And you see the striking increase in rainfall during the wet in the Kimberley and the Northern Territory of North Queensland. So it's definitely wetting up quite strongly. But you see drying in Tasmania really strongly during the summertime, a bit of drying along the southern rim, southwest WA, and you see that Queensland coast drying appearing as well. Now remember, that's seasonal, so that's during the warm season, that's during the summer season. But if we look at winter, this is where we see the climate change signal more strongly. There's the winter pattern. You still see it's getting wetter in the dry. In other words, you're getting more wet rainfall during the normally dry periods in the north. But you're seeing now pronounced drying in southwest WA, driest on record in many of those areas. And you're seeing some really dry areas in Victoria and southern New South Wales, down in the Alpine region and so on. That's a real concern. That's the southern part of the Murray-Darling Basin that generates most of the water for the whole basin, and that drives a lot of our agriculture. Now there's growing evidence now that that is linked to climate change. It's probably linked to the wintertime fronts that come off the Southern Ocean. They're slipping further south as the Hadley cells intensify. So there's good evidence that that is indeed a climate change link. So in terms of future, there's still a lot of uncertainty about what's going to happen in the north. The best projection is it's going to get wetter, although some models say that this trend we're observing may turn around. But the models are getting better for the south. So the projections are from the BOM and from SIRO. Average rainfall in southern Australia is projected to decrease as we continue to go into the future. Heavy rainfall, these big events that cause flooding, is projected to increase over most parts of Australia, but probably not in the areas where the drying is most pronounced. So that's the bottom line. So where we are seeing droughts now over the past couple of decades, we're likely to see more. And where we're seeing rainfall, it's not altogether a good story because that rainfall is likely to come down in more intense bursts rather than steady rainfall. So that's the story now, our best understanding of the water cycle around Australia. I'm going to close talking about coastal flooding. Some of you may have seen that the Council released just this past week a major report on coastal flooding. Got an enormous amount of coverage because we started putting some hard economic numbers on what this is actually going to cost if we ignore climate change. So basically all our effort now on the science is to focus on what are the risks if we don't do something about climate change, and hopefully people will move on very quickly to what we can do, which is the major theme of this meeting. But every so often you just need to remind people why you actually do have to change. So in terms of coastal flooding, this is the story quite simply. You get floods anyway along the coast. They're unusual events, but they happen when there's an unusually high tide coupled with a storm surge, a cyclone up in the north, or an east coast low off the east coast, or so on, some intensive low pressure system. And that's a little cartoon is showing what happens. But when you raise the whole sea level, you're pushing that system up. And what that means is that the normal floods that happen once in 100 years are going to happen far more frequently, they're going to penetrate farther, they're going to flood more. We actually see this already. This isn't theoretical. We have tide gauges in 2 places long enough to see it. One's in Fremantle and the other one's in Fort Denison in Sydney, and they've both seen a 3-fold increase second half of this past century. so it's already happening. These are the projections of the IPCC. Interestingly, although people complain that they may be too conservative, they in fact are about 25% higher than they were in the fourth assessment reports. They've moved them up. They've changed the baseline to the year 2000 rather than pre-industrial, which makes it look not so bad, but in fact it's pretty serious. We're tracking at the upper level now in terms of emissions, so we're tracking toward anywhere from 0.6, 0.7 to a meter by 2100. But a lot of people say, well, isn't sea level rise inevitable? Yes, a certain amount is, but bear in mind what we do about getting emissions down will have a huge impact on the frequency of flooding. If we can really meet this 2-degree target, if we can really decarbonize economies by 2050, we'll be down in that blue or purple range. And we may have a shot of limiting the rise to about half a meter by the end of the century rather than meter. Makes a huge difference to people, to property, to infrastructure, and so on. So if you look at the increase in flooding frequency now, if we take our business as usual, that's the bad one, you can see the size of those dots and you can see those numbers. They are really, really high. I won't go into the reasons why those multiplication factors are so high. We saw them on Wednesday at Sydney Harbour and Darling Harbour. You can see it absolutely clearly when you look at flooding marks on the walls, on the seawalls, on the pylons, and you see those little dots that go up higher. Well, that 1 in 100 one is that little dot up higher. But you go down 20 or 30 centimeters and you get an enormous cluster of dots. So basically, we like to live near the sea. We build property and infrastructure as close as we can to today's tides. But very modest increases in sea level give you those multiplication factors. It's easier to understand this way. Look at Sydney. So this is 1 meter sea level rise. 1 meter, it's about something like that. A 1 in 100-year event that the engineers plan for is going to happen every day or so. In other words, every time the tide comes up, it's going to slosh on your infrastructure. It's unviable. Other places are just as bad. Bundaberg, Darwin, Hobart. The best ones is Adelaide. It's only 100 times. So that means that the 1 in 100-year event you have to mop up only every year. Lucky compared to Sydney. And so you can see some of the other ones. So this gets the notice of the economists. Now Brisbane actually doesn't appear here. We don't have a tide gauge that gives us long enough record to actually be able to look at this. This is based on actual tide gauge data. And it differs from city to city. That's why the numbers are different. But Brisbane is not immune. I flew in last night to Brisbane Airport. Most of you here have probably flown in or out of Brisbane. It's near the coastline. It's a low-lying piece of infrastructure. It's a congested airport with delays, so they're building another runway. It's already under construction. But the people at Brisbane Airport actually did the right thing. They said, all right, this runway has to be viable for a long period of time, well into the second half of this century. We know sea level is rising. We can't ignore it. So they went to the scientists in Hobart who understand sea level rise, got the best advice, came back and told their beam counters that their planning for the runway was far too low. And of course the economists screamed, but the airport did the right thing and said, we need to have this viable. We are not prepared to take the risk, given the scientists' understanding. We're going to build this not at 3.2 or 3.3 meters above mean high tide, but 4.1. Big additional expense, but they did that to make sure it was viable. So there's a point here. If we don't do something about climate change, even adapting is going to entail huge economic costs. The next step of our economic equation is to compare those costs. People say, well, you can adapt, but it costs you to adapt. Compare those costs with the cost of putting in renewable energy systems, and that price is coming down all the time. So the whole equation is tipping now, economically, in favor of early and vigorous action to get emissions down. So although this is still the impact, it's still a bad part of the story, it's part of the equation. It needs to be told so that you can convince the hard-headed economists that we're going to save bucket loads of money by getting emissions down now, not by having to rebuild and redo infrastructure. It's going to cost us a lot more money. It just makes good economic sense. Okay, what about the big ticket item? Greenland, West Antarctica, could it make things even worse? The answer is probably yes, but probably not this century, given inertia in the system, but probably next century. Now the IPCC for the first time put some actual numbers on the tipping point question. And that is the point past which you're going to lose Greenland no matter what you do. To me, the numbers are really scary because the low one is 1 degree above pre-industrial. We're virtually there now. The high one is 4. It's probably in between. That's the best guess. But even 2 degrees could be really dangerous in terms of losing Greenland. So there's a real pressure now to get emissions down. Greenland is equivalent to about 7 meters of sea level rise. It's not going to happen tomorrow, but it means you're committed to ongoing sea level rise of a very high rate for centuries if you tip Greenland. So again, the science there is stated very calmly, but in fact it's sending out a very, very big warning on the sea level rise issue. That's what it looks like now. We're seeing melting more commonly during the summertime in Greenland on the ice sheet. We're losing more from outflow from the glaciers, about 50-50 in terms of where the additional water is coming from pure melt and from glacial discharge. If you look at what's happening, Greenland and Antarctica, mainly West Antarctica, are losing ice. The black line is the sum. You see the rate of that ice loss is increasing over the last couple of decades. So the polar ice sheets are playing an increasingly prominent role in addition to thermal expansion of the ocean in the sea level story. Okay, I just want to close by pointing out something that was just loaded up yesterday or the day before on the Climate Council website. I strongly encourage you to get this. It's not a sciencey thing like I like to do. It's something done by Amanda, who's very, very good at communicating. And what she's doing is say, how do you communicate climate change in Australia? How do you put forward these risks? How do you match the problem to the opportunities and the solution? I think it's an excellent document. I actually go to it myself to learn how to better communicate the stuff I do. It's downloadable, and if you just, I'll click over there, that's the website. Just go onto that website, very easy, climatecouncil.org.au, and look for that document. Very readable, good examples of how you deal with skeptical questions, myths, but really how you put forward the opportunities and how you paint that in a way that shows that the costs, the economic costs, the social costs, the personal costs of not doing something of now getting so great that it should be obvious to anybody that the only smart thing to do is get on top of this problem really quickly. Okay, well hopefully that's all you got to hear today and tomorrow about the problems, but I hope that gives you some little bit of context for discussing how we get on top of the problems. So thanks very much.